Hello, ladies and gentlemen, and welcome back to our Canadian Senior Contest from the year 2015. We're on question number 6, A6 to be exact, the last question in Part A. And the Part A questions, although they are final answer, you'll find that 5 and especially 6 can be quite difficult. I sometimes find A6 to actually be the second hardest question on the competition, usually much harder than B2. B3 still takes the cake, of course, but A6, it's quite a difficult one usually. And I think this year's is no exception. I do remember when this one was written, and I think we had a heck of a time with A6 trying to figure out a good way to do it. When we saw the contest, the next week we had to sort of show solutions to our local enrichment program, and we had a heck of a time trying to come up with a way to do this that we think was accessible to the high school kids. Anyway, let's dive into this question. Suppose that x and y are angles, with tan x is equal to 1 over m, and tan y is a over n, for some positive integers a, m, and n. Determine the number of positive integers, a less than 50, for which there are exactly 6 pairs of positive integers, m, n, with x plus y is equal to 45 degrees. And then they tell us the formula tan x plus y is equal to tan x plus tan y all over 1 minus tan x times tan y. That might be useful. Okay. So, there's not a whole lot that is apparent for this question. First things I'm seeing is x plus y is 45 degrees, and they give us a tan formula. They actually say tan of x plus y in the question. I'm betting we're probably going to have to plug in 45 degrees in there. Fortunately, tan of 45 degrees is a 45 degrees is a nice simple angle. Tan of 45 degrees, you should hopefully just know that it's 1. Okay, tan is sine over cos, and 45 degrees is exactly the first time that sine and cos are equal to each other. Their graphs cross right there. Okay, so I'm guessing that 1 is equal to, and then we've got our 1 over m, and then our a over n's, and we can use those, and we'll get some formula relating m, n, and a. Okay, the other thing I'm noticing here is we want exactly 6 pairs of positive integers. Okay, and when I think about that, I'm starting to think, well, how do I enumerate pairs of positive integers? Where does that come in? And as I think about it, and knowing that we're probably going to get some equation relating a, m, and n, we're probably going to get something like, just off the top of my head, something like a is equal to m times n. Just let's suppose that were something we were to argue we were able to work around and get to. A is equal to m times n. Well, then we'd need to find pairs of integers m and n that were factors of a. And so to get exactly 6 pairs, we would want numbers a that had 6 pairs of positive factors. And there's a way to enumerate factors. So already I'm thinking, first of all, that we got to plug in x plus y equals 45 and use tan of 45 as 1. But that the resulting equation I get, I'm probably going to want to start thinking about it in terms of being factored. Okay? That's the idea. That's what I'm thinking. So let's dive in and we'll execute some of these plans here. So we'll take the x plus y is 45, and we'll plug that into our tangent formula. So 1 is the same as tan of 45, and that's tan of x plus y, but that's tan of x plus tan of y all over 1 minus tan of x tan of y. But they gave us formulas for tan x and tan y. Tan x was 1 over m. Tan y was a over n. Down here we've got 1 minus 1 over m, a over n. So I'm thinking get a common denominator on the bottom, and also on the top, I guess. So n over mn plus am over mn all over mn over mn minus a over mn. Okay, well, we can combine all that. We get n minus am over mn all over mn minus a all over mn. Now, when we work this out, if you want to, you can introduce an intermediate step where you invert the denominator fraction and then multiply these two. But the mn's are going to cancel out. And we're going to be left with n minus am. So 1 is equal to n minus am over mn minus a. I think that was right. Let me just go back and double check. Yeah, mn minus a down there. Okay. And that's all equal to 1. Well, if those are equal to 1, then I must have something divided by itself. Otherwise, how are we going to get equal to 1? So that tells me that mn minus a is n minus am. Okay. So we've resolved our sort of x plus y equals 45 degrees. We've used the tan and everything like that. So we're doing well. Okay. So now I think it's time to bring in that factoring idea and, number of divisors into play. I have an equation here relating m, n, and a. If I want it's the numbers a that I want to pick, and then from my choice of a, how many m and n solve this equation. That's sort of what we're down to. So my a's are what I need to pick. Maybe I'd like everything in terms of a, or maybe I'd just like a on one side. We have one equation and 3 unknowns. I don't think we'll be able to solve for m in terms of a and n in terms of a, but I think we can rearrange this and just get a equals on one side. I think that would probably be a good idea. So let's try and do that now. So I can bring the am over here. So we'll get am, keep the a over there, and then n, we'll bring the mn back over here. So I've got a m minus 1 is equal to n 1 minus m. Okay. And, interesting. I can rearrange that and say minus n is m minus 1, and we can then say a is negative n, dividing by m minus 1 on both sides. What to do from there? So we've got a is equal to minus n. That doesn't seem right. Why doesn't that seem right? We want positive integers a and 6 pairs of positive integers m and n. I've done something wrong. What have I done wrong? Tan of 45 is definitely 1. Something's not right here. Tan of x was 1 over m. What has gone wrong? N minus am, mn minus a. N minus am, mn minus a. mn minus a has got to be equal to n minus am. Brought the am over here. Brought the mn over here. Took out a factor of n, took out a factor of a. Divided both sides by m minus 1. Unless m is forced to be 1, in which case we can't divide by 0, I've done something wrong. That's fine, that's fine. We'll get tan of a and a over mn down there. We'll get mn over there. Oh, I think I see it. This should be a plus sign. Copied it wrong. Oh, geez. Good, I was wondering what was going on with that. I had a gibberish answer. There we go. Okay, so found my mistake, and it's always good when you see a mistake. Here, listen to me act like that was on purpose or something. But it's always good when you think you've got a gibberish answer there. We had A had to be negative n, but both A and n had to be positive. That didn't make any sense. So I stopped immediately what I was doing, and I tracked down my error, and it was a plus sign. Okay, we're back in the game. We can bring the n over to this side, and we can bring the A over to this side. Alright, so now we got n, m minus 1 over here, and a m plus 1 over here. So I'm hesitant to leave it with the division here, but I do now have a all by itself. But I think I'd actually prefer it as a m plus 1. And the reason for that being maybe, yeah, I think I want to leave it like that. Just because whatever this number is, we're still looking for two factors. And for each pair n and m over here, or for every pair of factors we can get an n and an m minus 1 out of there. So that will do just nicely. But where do we go from here? Well, okay, let's suppose that I did use the a equals. A equals n, m minus 1 over m plus 1. Could I substitute a back in, and would that be meaningful in any way? I don't think so, because I'd just be subbing it in and I'd get 0 equals 0 on both sides, something like that. Or nm equals nm, or something like that. Okay, so I've got, this is the only thing I can get after all the long-winded details they gave us in the problem. This is ultimately all I've got to work with. So we want positive integers m and n. Okay. Well, should I be solving for everything in terms of a? Maybe what happens if I try and get I can get m minus 1 over m plus 1. I can get that to be a over n. And if that's tan y, isn't it? Yeah, divide by n, divide by n plus 1. I can get this as an expression for tan y. And tan x was 1 over n. Does that help? If I plug that back into the original equation, will that allow me to solve for m? Or will that just get me a 1 equals 1 on both sides, giving me, again, a pointless answer? I think we should take this equation here and just try and get an a with some m and n's that do work for this. Okay, let's pick an a that's got a lot of factors. How about we let a be 12, and let's let m be 2, so that m minus 1 is 1, and then m plus 1 is 36. Then n being 36 would work. Okay, so that does, I mean, that's an answer of, that's what happens when a is 12. Tricky, tricky, tricky. Okay. I didn't want to do this because I don't think the division will be the right way to go about this. But if I just write a like this, a is an integer, which means we've got n and m minus 1 and m plus 1 here. So, for this expression on the right to be an integer, we need m plus 1 to divide n times m minus 1. So that's useful to know. And I think m plus 1 and m minus 1, sorry, m minus 1, not n minus 1, at best they have a GCD of 2, a greatest common divisor of 2. They differ by 2. And if d divides, just talking about divisors here, if d divides x and d divides y, then d divides, x minus y and y minus x. So suppose we had a divisor, something that divides m plus 1 and m minus 1. Then it would have to divide their difference. So it would have to divide m plus 1 minus m minus 1, which is 2. So d would have to divide by 2. D would have to divide 2. So either m plus 1 and m minus 1 are both even, or they're odd. And I think if they're both odd, okay, if they're both odd, they have a GCD of 1. Okay, which means that no part of m plus 1 is a factor of m minus 1. That means n has to have all the factors of m plus 1 in it. Because remember that a is an integer, so n divided by m plus 1 has to be an integer, because there's no way that any part of the m plus 1 is going into the m minus 1. So I think we might have some casework. Okay, so we'll say what happens if m is even? Then m plus 1 is odd, m minus 1 is odd. They have a GCD of 1. And so m plus 1 has to completely be a factor of n. And I think that'll be something. And then we'll switch gears and say, what if m is odd? If m is odd, then we get an even number, and we can account for the fact that one of the factors of m plus 1, that 2, has got to be in m minus 1. And that's the only factor that can be there. Okay? I think this might be a good way to approach it. Okay. So I was mistaken that, I thought having it equal to a and having that division there would hurt. Looks like that's going to help us. Okay, so we'll just erase my other workings there. So I think this is probably the way to go. So let's work at the easy case first. Or at least I think it's the easy case. So if m is even, m minus 1 and m plus 1 are odd. They have a GCD of 1. So we know m plus 1 divides n times m minus 1, but if m plus 1 and m minus 1 have a GCD of 1, that tells us that m plus 1 completely divides n. I'm supposed to be right, but I was about to write k equals n divided by m plus 1. Okay. So a we can write as k times m minus 1. So what happens here? If we have a and we choose it so it has we can make m minus 1 any of the odd factors of a. And then That'll solve for m. And then once we know that m, we'll know what k is. It's the leftover factor multiplied by m plus 1, and that will definitely get us an n. And so for every odd factor of a, we get an m minus 1. Because remember, m minus 1 has to be odd because this is the case where m's are all even. And so that solves for m. K is the leftovers. And we use our m to solve for n. Okay. So now we're picking a's, and the number of odd factors that it has gives us a pair m and n, and these will have to be distinct. So every odd factor gives a unique m and n. All right. So that's what happens if we're just looking at m's being even. We'll get an even m. M minus 1 is going to be odd. That's a factor of a. We'll get our k. We'll get our m. And then from those two, we get our n. That gives us a pair mn. All right. So now we know when we're looking at those numbers, our possible values for a being less than 50, anytime we see a number like 15, which has 1, 3, 5, and 15, that's 4 odd factors, each one of them gives us a brand new pair mn. All right? Each one gives us a brand new pair mn. So now what happens if we look at m minus 1 being even? So m is odd, so this is our other case here. So m is odd, that means m minus 1, m plus 1 are even. Okay. So, in this case, what can we do? Well, we can write, we know that m minus 1 is even, so let's let it be 2 L. Then m plus 1 is equal to 2L plus 2. Fine there. And then A is going to be n over m minus 1. Or n times m minus 1 all over m plus 1. Which is n times 2L over 2L plus 1. Those ones go away, and now we've got n, L, and L plus 1. And L plus 1 has to completely be a factor of n, because L and L plus 1 have a GCD of 1. So I'm running out of letters, but let's let J be n over L plus 1. So then A is going to be equal to J times L. Okay, now for each factor L that we have, we can multiply it by 2 and we'll get an m minus 1. So 2L plus 1 is going to be m. Okay, and then and j, L plus 1 is n. And this gives us brand new pairs m and n. Okay. So, I think every factor, based on this last case, every factor of A contributes a pair m and n. And if we go back to the previous case, every odd factor contributes another pair. Okay, the only question is there overlap here? Well, in these cases, in the most recent ones, the m that we get is going to be odd. And in these previous cases, the m that we get is always even. So I don't think there'll be any overlap. So let's take this for a test. Let's do an example. A is 12. What are the factors of 12? We got 1, 2, 3, 4, 6, and 12. So 1, 2, 3, 4, 5, 6 pairs for m and n. And then how many odds? Just 1 and 2. So there should be 8 pairs m and n here. Let's work these out and make sure that there's no overlap. Okay, I'm pretty sure there's no overlap, but I don't want to have missed something or screwed up the theory. I think if we've done this right, we've accounted for every single possible m and n we can get. I just want to make absolute certain that there's no overlap. So that way when I count it out, I'll know how many factors to count, and then I'll also count out the odd factors. And since a's got to be less than 50, we will just we'll go ahead and write out the factors. I'll see if I can think of a faster way to do it. There might be a faster way. Heck, I might not even be doing the way they do it. If I recall correctly, because I was down there for the marking for this one, the solution that they gave us for the marking, I don't think I saw anyone do it, but I think it involved you multiplied by 2a, and that made this counting factor thing a lot easier. But as I can't remember it, and I didn't think it was particularly organic, I think the way I've done it is a little more natural to think about it. I decided not to reproduce it. I try and just actually do the contests as I would for you guys. Okay, so let's double check here. So for if L is 1, okay, we're gonna go over to another page and we're gonna make a big chart. So 1, 2, 3. What's gonna be our for this one? It'll be L. We have an M and we have an N. 4, 6, 12, and then for our odd factors 1 and 3, what's going to be our m minus 1, our m, and our n. Okay. So this guy here is our L. So 2L plus 1 is m. So that's 3, 5, 7, 9, 2 times 6 is a 13, 25. And then, so that's 2, 3, 4, 5, 7, 13. it's L plus 1 times the remaining factor. So I guess J is what we need in here as well. J, 12, 6, 4, 3, 2, 1. So N will be 13. The 24 here. 18. 16 here. 15. 14 here. So for these ones down here, the ones coming from the M is even case, we'll get 2, we'll get 4, M minus 1. These guys are M minus 1. The remaining factor, which I think we called K, is 12, and in this case it's 4. And so you had to do M plus 1, which is 3 and 5. We got 20 and 36. Okay. And hey, that's the 2 and 36 that we worked out earlier. So, all of these are fairly unique. I do have 8 of them. What I'm going to do is I'm just going to grab my calculator, pick one at random, and make sure it actually satisfies the results. Okay, so I'm looking for 45 degrees for my x plus my y. So let's pick m is 7 and n is 16. And in this case, a is 12. So what was it? 1 over m. That's supposed to be tan x, so I'm going to inverse tan that. And I get, I'm writing it down on this page here, but you guys can't see me because you can't see it because you're watching me. Hi. I get 8.1301 degrees. That's for m is 7. We did 1 over 7. Okay. And then it's over 16. 12 over 16. We got 0.75, and we tan inverse that. And I get about 36.8698. I'm going to add to that, so 36.8698, added 8.1301, 45.09999. Did I enter those in right? Oh, I put a 96. 36.8698 plus 8.1301, 44.99999, which would be 45 if I probably had the actual numbers. So these work, and I'm getting unique pairs m and n. Okay. So I've got a theory that works. Great. Now I need to narrow down my numbers from positive integers a less than 50. Okay? So that's all the work that needs to be done now. So just for a number, we count up how many factors and then count how many odd factors. Things I can do, I think, to rule out. So let's count. So first thing, I think no primes will work. 2 doesn't work. But any other prime is an odd prime, and it's 1 and itself. Both of those count, and then they're odd, so they count again. But that's only going to be 4 pairs m and n. So no primes, so we can skip all the primes. So now we're looking at numbers like 4, 6, 8, 9, 10, 11 we can skip. 12 we've done is 8. So 8 of those. Let's do a few more and see if we notice any patterns. So 4 has 1, 2, and 4. That's 3 factors plus 1 odd one. That's going to be 4 pairs. 6 has 1, 2, 3, 6. So that's 4 factors and 2 odd factors. That's 6. That's a good one. We like that one. 8 has 1, 2, 4, and 8. It's 4 factors plus 1 odd one. That should be 5. 9 has 1, 3, and 9. That's 3 factors and 3 odd factors. That should be 6. 10 is 1, 2, 5, 10. So that's 4 factors and 2 odd ones. That's a 6. So we're getting some actual answers here. It's looking like, I think, 2 times a prime an odd prime, we'll always have 1, 2, the prime, and 2 times the prime. That'll be 4 factors plus 2 odd ones, so that'll be 6. So that helps. And 9 here. How did we get 9? It was an odd prime squared. And that has factors 1p and p squared. And that's also going to give us a 6. So 2 times 3, 2 times 5, 2 times 7, 2 times 11, 2 times 13, 2 times 17, 2 times 19, 2 times 23. Those are all the 2p ones. And then 9 and 25. Those are all the odd primes squared. So now we don't need to look at these ones anymore. And we don't need to look at odd primes. So we've got 15. I think that'll be too many. 16, 17 won't work. 18 maybe. 19's a prime, so we don't need to worry about that. 20, 21, 22's on our list. 23's a prime, so that's no good. How about 24? 25's on our list. Same with 26. How about 27? That's a third power of an odd prime. 28, 29 we don't need to consider. 30, 31 we don't need to consider. 32, 33, 34 is on our list. 35, 36, that's going to be way too high. 37 is a prime. 38's on our list. 39, 40, 41's a prime. 42, 43 is a prime. 44, 45, 46 is on our list. 47 is a prime. 48. Oh, 49 is another odd square. And 50. Okay. So only a little more to go. 32 is going to have 1, 2, 4, 8, 16, and 32. That's 6 of them and 1 odd factor, so that's going to be 7. But that gives me hope for 16. 1, 2, 4, 8, 16. That's 5 of them and 1 odd. That makes a 6. So that's another useful one. 1, 3, 5, and 15. That's 4 factors, but all of them are odd. So that's a no-go. That's going to be 8 of them. 1, 2, 3. If ever I list out more than 6 factors, it's not going to work. So if 18 doesn't work, 36 will have even more factors, so that definitely won't work. 3, 6, 9, 18. That's 6 of them, but there are a couple odds, so that's no. And that means 16 is no. While I'm over here, looks like if I have P and Q odd, we get 1, P, Q, and PQ. And that's going to be 8. So that means 39's off the list. That's why 15's off the list. 21 will be off the list. 33 will be off the list. 35 will be off the list. This is a great way to cancel some of these things out. 20. That's 1, 2, 4, 5, 10, 20. And there are some odd ones in there, so that's not going to work. 24. 12 had 8, so 24 is definitely not going to work. 27. 9 is on our list. It's going to have even more factors, so 27 won't work. 14 is on our list. 28 will have even more factors. It won't work. 15 had 8 factors, so 30 will at least have an extra factor of 30, so that's 9, so that won't work. 32 we said won't work. 40 is, 20 won't work. That's too many, so 40 will have even more, so that won't work. 21 had too many, so 42 will have too many. 45 is a multiple of 15, so that also won't work. 22 is on our list. It has exactly 6, so 44 will have at least 7, so that won't work. 24 didn't work, so 48 won't work. And 25 is on our list, so 50 won't work. And we already said 36 won't work. So, turns out 6, we'll do a summary here, but I'm actually kind of surprised at 16 that 16 worked. But, so what do we got? 6, 10, we also had 9, 25, 45 in that weird anomalous case of 16. That sort of came out of left field. 10, we had 14, 22, 26, 34, 38, 46. I don't think I'm missing any. Nope, we're good. So there's 8 in the first list, 3 in the next list, and 1 in the next list. So it should be 12 values of A give 6 pairs MN. Ooh, okay. So I think that should be the answer. Yeah, we went through every number. We ruled them out. We ruled out the primes. We ruled out P times Q when they're both odd. That certainly made our lives a lot easier. But I think that's it. I think that does it for A6 on the 2015. And yeah, if you get a chance, go. I mean, you can click the link in the description, go to the Waterloo website to get a copy of this contest if you haven't already. But you can also get their solutions and go read their solution. See if you prefer theirs to mine, because they multiply, I think, by 2A, if I'm remembering correctly. It was a year and a half ago at the time I recorded. But I think they multiply by 2A, and I don't think they really motivated that. I don't like that. I didn't like that. Didn't feel organic, like a student would just say, aha, we multiply by 2A. But, I mean, maybe you did it that way, and maybe you agree, maybe you find their solution simpler, in which case I would love to hear about it. So leave a comment below one way or the other which solution you prefer. And either way, I'm going to move on to B1, so I'll see you guys for that one next time.